In the last segment, we were introduced to the de Broglie relationship between the momentum of an object and its wavelength, which applies both to massless particles, photons, and massive particles such as electrons and neutrons. And in this segment, we want to explore a bit more what this means for the diffraction of electrons. Suppose that we wanted to have an electron with a wavelength of about an angstrom. That sounds like that would be suitable for Bragg diffraction. What kind of energy and velocity ought it to have? Well, we can turn around that relationship between the wavelength and kinetic energy, solve for the kinetic energy using Planck's constant, the mass of the electron, and the wavelength that we want. And we get 2.4 times 10 to the minus 17 joules, which probably doesn't convey a whole lot. In electron volt units, that's 151 eV. And I'll remind you, an electron volt is the energy that an electron gains by passing through a potential of 1 volt. So this says it would only take 151 volt potential difference to get electrons to that energy. That's easily achievable. Now, in fact, electron microscopes typically operate at much higher potentials for technical reasons. That gives them smaller scattering angles, but this says that this is sort of the minimum energy that we'd need. What about velocity? If lambda is h over mv, then the velocity is h over m lambda, and we get something like 7 million meters per second, which is pretty fast, but still a lot less than relativistic velocities, which said that we were justified in using the non-relativistic formula. So as I mentioned, the most common use of this is in an electron microscope. In a transmission electron microscope, electrons are accelerated to high voltage, and then there's a variety of components that are focusing and collimating the beam so that it strikes a sample, and then you can either measure the straight through beam or you can measure diffracted beam. So these can actually operate in two different modes, and you measure what comes after. That's transmitted through the sample. That's why it's called a transmission electron microscope, or TEM. TEM can do both imaging and diffraction. What do I mean by that? Here is an image of a snowflake. So you can see here the scale, 500 microns. This is pretty small. So this is just what you would imagine if you actually looked at the thing with sufficiently high resolution. That's what you'd see. But you can also then focus in on a particular spot and get a diffraction pattern. So this electron diffraction image of tantalum oxide is very similar to the kind of image that you might have gotten using X-rays, as we've been discussing extensively. So why would you use electrons or X-rays? Well, compared with X-rays, electrons can look at very small samples. That is to say, you can focus in on a very small area, really just a few, sometimes just a few atoms across. It also tends to be a surface-sensitive technique, as we'll see in a second when we talk about low-energy electron diffraction. So that can sometimes be good. One of the biggest problems with electrons is that because of multiple scattering, it can be harder to quantify the scattered intensity. In our whole discussion of Fourier transforms and X-ray scattering, we were using the square roots of those intensities to work back to the structure. That's harder to do with electrons because of the multiple scattering problem. In general, you need to have your sample in a vacuum. That's sometimes a problem. It's somewhat more likely that you're going to have some combination of heating or radiation damage to the sample because the beam is typically focused down to a very small area. And a more subtle problem is what you can sometimes call selection bias, that you're scanning your electron beam over your sample until you find something that looks interesting. And so the tendency is to stop when you get something that looks interesting or looks like what you were expecting, which is not necessarily representative of the entire sample. On the other hand, you know exactly where you were when you got that, as compared with X-rays where you have to measure the entire sample all at once, including possible multiple components. So there's advantages and disadvantages both ways. As an alternative to transmission electron microscopes, which are done with high energy and in transmission, there's a technique called low energy electron diffraction, or LEED. Since you have relatively low energy, you have large wavelengths, which means that if you're going to get Bragg scattering at all, it's going to be at very large angles. So this is most often used as a surface probe. You have some kind of surface like a metal or a semiconductor or something like that. You direct electrons on, you see what comes off, and as you can see here, this is the nickel 111 surface with and without hydrogen adsorbed, and so you're actually looking at how the top layer of atoms are rearranged. So this is a standard technique in surface science when you're looking at surfaces of things like metals. Here's a good book on transmission electron microscopy and goes into much more detail than I've been able to present here. And I can also point you towards a couple of Wikipedia pages that are also helpful.